Okay, so in today's lab, we're going to study the periodic table in detail. You guys have already done the classes on this, so this should be more of a revision. The first simulation is going to talk about filling the gaps in Mendeleev's periodic table. Do you remember this? Sort of, kind of? Mendeleev predicted a lot of things and he left a few gaps. Remember all that? Okay, all right. So that's what we're going to do today. So on top you see a few names, yeah, like on the right hand side of element there's Eka boron, Eka aluminum, and Eka silicon. So Eka means like, and like boron, like aluminum, and like silicon. Boron, aluminum, and silicon were known elements at that point in time, and these guys were not known. Okay, the ones in orange. All right. So he predicted that, well, at some point in time they would exist. Yeah, that was the cool thing that he did. And because of what he did, later on these elements were found out. So using some sort of simple math, we can also figure it out. Uh, I'll tell you how that works. Yeah, you can see that there's some predicted atomic weight, predicted specific gravity. Notice that this black number next to each each element is its atomic weight. Over here is the specific gravity in blue. Specific gravity makes sense only if it's solid. Uh, Otherwise, it would be, gas is going to be really, really low, so we don't discuss that, okay? Cool. Specific gravity is the gravity, is its density with respect to water. Do you guys know this? Yeah? We've already done this in class when we did fluids. Okay, great. Cool. So, as you guys know, Mendeleev grouped elements according to their properties, right? So he took all the known elements and tried to fit them into his table, and he figured that there were gaps. So because of these gaps, he could do a couple of things. He could either admit that his theory was incorrect, but he was so sure about his theory, he said that these gaps were actually elements that had not been discovered. So he predicted their properties using some sort of averages, okay, law of averages. Very simple interpolation, yeah. It's called linear interpolation. You guys will learn about it later. Simply put, say something like Eka boron. Look at the third row with potassium, calcium, Eka boron, titanium, and vanadium. Yes, you guys know what I'm talking about? Yeah. All right, great. So in that row, it seems like it lies between calcium and titanium. So he said that the atomic weight of Eka boron would be exactly halfway between calcium and titanium. So that would be the estimated weight according to him was 40 plus 48 by 2. How much is that? 44. Exactly. Exactly. So that's what he thought. He also predicted that the specific gravity would also have a similar average. Can you guys tell me what that value would be? Same, the blue values for calcium and titanium, which is 1.55 and 4.55. Exactly. Now, exactly, using Dobereiner's triads, he used these ideas. Now, Dobereiner's triads also use the same interpolation idea. But the big thing was placing these triads, so to speak, in the table. So what his credit was, Mendeleev's credit was to place these guys in the correct order. Dobereiner's triads were talking only about vertical stuff. You remember? We had sodium, calcium, and sodium, potassium, and whatever was next, rubidium or something like that. Yeah, I don't remember at this point. Yeah, sorry, lithium, sodium, and potassium. That was one triad. Yeah, is that clear? So what was different between Dobereiner and this guy was that this guy predicted the entire table. Okay, not entire, but a large part of the table. Whereas Dobereiner was like, okay, he just figured that okay, these three guys form some sort of a, they have some sort of a linear relationship going, linear interpolation relationship. So yes, a very good spot, almost exactly like Dobereiner's triads. The biggest difference, as I said, was this arrangement. Okay, is that clear? Okay, great. So what is the specific gravity? What would the specific gravity of Eka boron be? If that of calcium is 1.55, titanium is 4.55, what would the specific gravity of Eka boron be according to this calculation? Same linear interpolation business. Very straightforward. Jacob, be careful. Yes, 3.05. Agreed? Does everybody agree with 3.05? Jayavardhan? Don't make me call out names. You guys are here in class, please participate. Okay? So the specific gravity is 3.05 and the weight that we estimated was 44. Let's let's do that. Okay, I'm going to change this predicted atomic weight to say 44. There you go, and predicted gravity to be 3. Yeah, because there's no 3.05, so I'll make it 3.1. Or let's stick to 3 at this point. Okay, and then you click on Eka boron, and let's see. I want to confirm. Okay, this is this button. When I click on confirm, there you go. Later on it was found out that Scandinavian, no, not Scandinavia is a country. Scandium, the atomic weight was 45 and the specific gravity was 2.99. That's very close to the predicted values, and use simple linear interpolation, nothing very fancy. So these things were later discovered when some fancy instruments like the mass spectrophotometer the mass spectrometer was invented. Remember, I mentioned this in class also. It's cool if you don't remember, but I'm just trying to say that this was figured out much later. Okay? Cool? So can you do a similar calculation now for, say, Eka aluminum? Now, use scandium, what we've just discovered, and yttrium, yeah, Sc and Yt. Can you use those both and give me the value of Eka aluminum? Yes? So, okay, couple of values. Why are you giving me different numbers? Give me one number and it should be unanimous. Is this addition of two numbers, a division by 2? That's okay. That's all right. 66.5. Okay. So that was 66.5. And what is the specific gravity? 3.73. Okay. I'm going to take that 3.7. Oops, sorry. One moment, guys. Okay. And I'm going to let this confirm go. Go to Eka aluminum and confirm. Now, what we did, hey, so as you can see that this worked out for the atomic weight, but not so much for the specific gravity. You see that? Yes? Okay. So now this was to show you that this law works at some times, but sometimes it completely fails. Why? Because there are some things that could not be explained. Remember, as you're going down, you expect the specific gravity to keep increasing. But you see from here, between this row and this row, there's a sudden drop in specific gravity. Yeah, massive drop in these two elements at least. Yeah? So you know that Mendeleev wasn't completely perfect. So how do you justify this Eka aluminium? I'll tell you. So what you can do is figure out the basic ideas between, yeah, you can find out Eka silicon and then back calculate and get Eka aluminum. Agreed? I can also do it that way. No harm, right? Okay, let's do that. Let's do that and see if you get a closer value. So you have to keep checking. Yeah? So let's now do titanium and zirconium and get Eka silicon. By the way, this element was gallium that we just figured, Eka aluminum. Can you do the same exercise with titanium and zirconium? 69. Okay. And what about the specific gravity? Just one moment, guys. 5.53. Okay. Sounds good. Sounds good. Let's see. I'm going to go ahead and make it 5.5. Here you go. And the weight you guys said was 69, right? One moment. We'll hit this. Ah, shoot. What is the specific gravity? 5.3, right? 5.5. I'm sorry. 5.53. Okay. One moment. It's difficult to do this with this mouse. Okay, here you go. Eka silicon. Oh, close enough. Yeah. See again over there. There's a slight bit of a difference, right? So what he did was quite, see for this it's closer than that. Yeah. The whatchamacallit, the specific gravity is completely off. But here at least it's somewhat close. Yes? Agreed? So this was a very crude technique, but without any fancy instrument, without anything, this guy figured out that this was possible, which is a really, really big deal. Okay? So these elements that were discovered finally were aluminium. I'm sorry, not aluminium. Hold on, one moment. That's just the guy who made the simulation probably put that there by mistake. Yeah, it's yeah. So these are all free simulations. This one's from Wolfram Alpha, very very cool site. Sorry, Wolfram demonstrations. So the elements that were discovered was Scandinavia, scandium, not Scandinavia, scandium, gallium, and germanium. Okay, this guy is a very very important of very it's very useful in the silicon industry. It's can be used. Have I taught you what doping is in terms of obviously chemistry? Yeah, I haven't. Okay. uh, you mess around with silicon in such a way to make it even more efficient in its job as a semiconductor. Okay, that's where this germanium would be really useful. Cool? Extremely important compound that was found out later. So this is some idea about Mendeley's periodic table, and you can see that it was perfect, almost bang on target with Eka boron, aka scandium. Eka aluminium or gallium, not so much. Germanium, yeah, almost there. All right. So he was pretty good in predicting that, okay, these guys exist. It's not that I've randomly made it up. You know, the properties somewhat off. The weights were almost bang on target, right? The specific gravity is a tricky. The density is a very tricky quantity. Yeah, mercury is a liquid. How did that happen? So that's a little tricky. It has a very high specific gravity, 13.6, but it's a liquid. So that part's a little tricky. Anyway, is this clear? Any questions so far in this simulation? Okay, so this method of averaging is basically called linear interpolation. As you can see, it's not entirely useful because I'm just taking the average of two values. There are other methods of interpolation that take into account the entire, like there's some way of interpolation like you use the entire table. You use something called a matrix and you do some funky math and you can actually predict the actual values. Okay, so that will take into account and you'll get a much more better number, which is what they actually use. We have used very simple linear interpolation, but you can use other mathematical techniques to actually get a much closer answer to the actual values. All right, is that clear? Okay, cool. I'm going to move on to the next simulation. Just hold on. Let me pause this and I will share the other window. Just one moment. So you can do many things with this simulation. It's a really, really cool simulation. The only changes I've made to the original simulation is I've marked cylinder. You can see this in many different forms. I've marked cylinder. You can see that these are all cylinders. All of these guys. If I rotate this a little bit more, you should be able to make out. Yeah? Cylinders that have a height. The larger the height, the higher the atomic number. Okay, because that's the property we're looking at this point. Clear? This is exactly the normal periodic table itself. Yeah, only difference is in 3D. You have helium, I'm sorry, starting at hydrogen, helium. So it's exactly the same table, alright? Don't get confused because of the dizzying bars. Yeah? So I can mess around with a lot of parameters. You can see that right over here. I'm going to stick to atomic number in the first one. In the first discussion. So you can see over here that atomic number clearly increases from the right. Yeah? Simple stuff. If I hold it up, you can see there's a slight increase from the left to the right. Right? Which is what we saw in the normal periodic table. So this is the normal periodic table itself. What is peculiar over here? Oh, I'm sorry, before I go to the peculiarities, the simple stuff. The atomic number also increases when you go down the group Agreed? The bars become larger and larger. Yeah, when you go from hydrogen to francium. So those are two common things. What's peculiar here is that these two bars, these two cylinders at the bottom are much lower than the dark pink one. You guys see that? Starts with La and Ac. These are the lanthanide and the actinide series that are special, yeah? Because the thing is that they have some very funky properties. Um, Basically, they don't really fit inside the normal periodic table, which is why they're placed outside it. All right. If you do want to know why and how, you'll probably have to take up science later on in the 11th and 12th. If you guys do that, you will learn more about this, why they're placed outside and all of that. But this was just to show that these guys are outside the periodic table, but they are not the end of the periodic table, right? There are more elements that follow after. How can I say that? Because the height, they're taller cylinders, right? The last one is LR, and the first one over here, RF, is taller than LR. Clear? So I can say for sure that that's not the end of the periodic table. So this is a very, very cool diagrammatic representation of the periodic table. Oops. Apologies. I seem to have turned around. Difficult controls. Okay, cool. So now if I change this atomic number to another parameter, say atomic weight. I've done that, just one moment. So it seems like it's similar, more or less the same, yeah? Hasn't changed too much from atomic number. Yeah? Same stuff. Very, very easy. So I'm not going to discuss it for too long. I'm going to change this to an interesting parameter called atomic radius. You guys remember what the atomic radius was? Basically the electron cloud that surrounds the central nucleus. All right. So I'm talking about one atom. I'm not talking about molecules at this point, not bonded stuff, just a single atom. Now, across the period, which means when I go from the left to the right, these bars are falling. You guys see this? Visually, it's clearly evident, right? From the left to right, the bars are decreasing, the size of the bars are decreasing. Why is that? Why does that happen? Recap from what we learned. Oh, very good, very good. Nuclear charge increases, but the number of shells remains the same. Yeah? Because you're adding electrons to the same shell. You need to say both of those together. Your answers is to the point, very good. But you need to add the nuclear charge increases, but the number of shells remains the same. Okay? Do you guys understand what Arjun just said? Everybody in class, please respond. Is this clear? Okay, great. Hey, Jayavardhan. Please don't make me call out your name. This is ridiculous. You guys have attended class for so long. Please participate. I'm not asking you tough questions. I'm just asking you to say yes or no if you've understood. Alright? That makes sure that I'm not talking to a wall. So please reply. Okay. So, we are adding protons to the nucleus, but the number of electrons added to the same shell. I mean, new electrons added to the same shell. Similarly, when you go down the group, the radius increases. This is because, why is this? Why does it increase down the group? Vertically, downwards. I'm saying the radius increases. That's clear. The cylinders have increased in height. Exactly. Each period in a periodic table represents a new shell. So as you go down the group, new shells keep getting added. And hence the radius increases. So good stuff. You guys remember, this is more of a recap of everything you've done in periodic table. Now if I change this property to boiling point, here things get a little tricky. All over the place. Yeah? Metals are generally solids at room temperature and have high boiling points. Metals would be, this is usually, that's mainly the middle guys, yeah? The left guys are an exception to this rule. You guys know that, right? The alkali metals and the alkali earth metals, they're an exception to the rule. But everything else in the middle, you can see are pretty high cylinders. The exceptions being carbon and boron. Why does carbon have the highest melting point? Any ideas? What's the deal behind that? Give me a physical example. I don't want you to go into chemistry, just an example of something, of some form of carbon. Diamond. Yeah, exactly. It's just diamond. Diamond has got the highest melting point and the boiling point as well. Clear? Why carbon is pretty high up? Boron forms similar structure. Hence is up there as well. Now, this, besides carbon and boron, and also leaving out the zinc, cadmium, and mercury, yeah, these are exceptions. You can clearly differentiate between the metals and the non-metals. Yeah? Leaving out carbon, boron, and this zinc, cadmium, and hydrogen. It's like you form a bit of a diagonal over here that separates the metals from the non-metals, right? That's why we did that I mean, some periodic tables have that diagonal thingy drawn. The actual diagonal is drawn all the way from boron to polonium, which means it goes from here. Yeah, it includes boron and carbon, and silicon, and germanium, and stannous, which is tin, and SB. I don't remember the name for SB, and polonium. So you see that there's a bit of a diagonal that's formed over here that clearly segregates non-metals from metals, right? Antimony, yes, that's antimony. Good job. So, yeah, is that clear? These guys in the middle are called metalloids. Somebody had asked in class what are metalloids. So these guys are metalloids because they're transitioning between metals and non-metals. In nature, everything is gradual, not sudden. Okay, that's the deal behind that. Cool. Let's look at some other properties that define metals and non-metals. GE is germanium. Yeah, germanium is one of the metalloids. Basically, the borderline elements are all metalloids. Let's look at something called thermal conductivity. You guys know what thermal conductivity is? Basically, the ability to transfer heat. Yeah? What do I mean by transfer heat? If I touch one side of the metal, if I add heat to one side of a substance, and on the other side, if I feel the heat right away, that means it's transmitted heat very well. Right? This is the reason why metals feel cold. And if I have wood, it doesn't do that. So although even if you have, say, an iron bar and wood at the same temperature, exact same temperature, say 27 degrees Celsius, iron feels a lot hotter. I'm sorry, a lot colder. Why? Because heat transfers from you to the metal. Okay? This could work the other way around if the temperature of iron or the surroundings were more than you. You understand what I'm saying? Because heat transfer always takes place from higher temperature to lower temperature. Extremely important. So the idea of what is cold and what is hot is very, very relative. Agreed? Do you clearly understand what is thermal conductivity now? Allows heat to transfer quickly. It has to do with time. Okay? Okay, great. So, the high bars are copper, silver, and gold. That's why a lot of your headphones, the ones that you plug into your phones or to your computer, so they have gold tips because gold is an excellent conductor. You can't have gold wires, hence very, very good wiring is made out of copper. Copper wiring also is really expensive, and these days only aluminum and some other things are used. Yeah, these days in wiring. Earlier, copper wiring was used, but as you can see, it's got a higher conductivity, but it's also very, very expensive. Okay, cool. That was that about thermal conductivity. Exception to the metallic rule, clearly mercury, zinc, and cadmium. Yeah, these guys are playing the spoil sport. They don't like being very good conductors, hence they're down there. Okay, now let's discuss another very interesting thing called fusion heat. What is fusion heat? It's basically the heat released when you convert from solid to liquid. Okay? Not heat release, I'm sorry, the heat required. Because I'm breaking bonds, clearly I need to give in heat. Does that make sense? Similar to, yes, exactly latent heat. Yes. Yes, both of you are correct. That's what fusion heat means. Heat of fusion, or yeah, same thing. Cool. Again, carbon's up there because of diamond. Boron's close by again because it forms a similar structure. Silicon, all of those guys are there. But otherwise, metals generally would have a high heat of fusion. As you can see, non-metals are completely low. Yeah, almost like close to zero compared to these guys. So there again, you have that whole boundary of metalloids and metals versus the non-metals. Yeah, clear boundary there, that diagonal boundary, you can see that again. Okay. This basically is trying to say that stronger the atomic force, the greater would be the energy that needs to be supplied to break the bonds. Physical bonds. Is this clear? As your friend said, latent heat. Okay? Alright, great. Moving on. Uh, let's look at another property. These are some basic things. Now let's look at properties that we have specifically learned in class. We learned some very interesting property called electron affinity. Electron affinity refers to what? Do you guys remember what is electron affinity? If you don't, look at the diagram. Think about what it could mean. This is where you guys give me a response. I'm waiting for a response. Wow, that was a very good answer, Arjun. And yes, Jayavardhan is the other way around, except an electron, Jayavardhan. Okay. So I think it should be energy released because bonds are being formed. It's a tendency to absorb an electron. That is correct. But if you talk about energy, you have to be very careful. So ionization potential is actually breaking of bond. So there you need to give energy. You understand? When I'm forming a bond, energy will be released. Okay? So, hence this definition makes sense because now you see chlorine, fluorine and these guys have really high bars, which means they release a lot of energy, which means they are really stable ions, anions, which means they readily want to accept an electron. Therefore, non-metals would have a very large electron affinity and metals clearly would have a low electron affinity. Alright? Exceptions again, gold, palladium, these guys are exceptions to that rule. Let's look at another very interesting thing, similar, very similar but not the same. Something called electronegativity. Electronegativity talks about a bonded pair of electrons. This is the main difference. Electron affinity, as your friend pointed out, has to do with a single atom, gaseous neutral atom. Extremely important. Electronegativity, as a bit of a recap, has to do with a bonded pair of electrons. What to do with a bonded pair of electrons? Well, the tendency to attract the bonded pair. Okay? And all of this is relative. Fluorine has the highest and it's randomly designated to be 4. Everything else is in relation to that. And francium happens to be the least. I don't remember how much it was, like 0.9 or something. I don't remember. But basically that's the deal. Yeah, it's a relative thing and you're comparing to fluorine. So lower the electronegativity, clearly it would form a positive ion. And if it's not possible for it to form an ion, it would form a slightly positive charge. Remember the delta positive and delta negative? Remember that? That had to do with electronegativity. Okay? Again, you can clearly distinguish between non-metals and metals here. Now, this is really interesting. Something we haven't discussed in class, but we should do so now. Let's look at universal abundance, or basically the ratio in which these guys are formed in the sun. Yeah, everything we do is because of sunlight. If there was no sunlight, we wouldn't survive. So the abundance of these elements in the periodic table in the sun is this. Yeah, like 90 or something like 80% of hydrogen and 20% helium. So where do the rest of them come from? Any ideas? What do you guys think? Not been explicitly taught in class. Okay, I get a few answers. Jayavardhan, what do you think? So, other stuff. No, innovative answer. But the closest amongst the answer that I've got is bond together. But their bonding requires a lot of energy, and sun has tons of energy. So hydrogen combines, forms helium. Helium combines, forms other atoms. Requires tons of energy, but this once you not electrons. This has to do with neutrons now, neutrons and protons. Yeah, scary stuff. Uh, because you more to form the other atoms from hydrogen and helium, to form sodium, to form lithium, I need to add protons. Yes. How do I do that? Hydrogen combines another hydrogen atom to form helium. That requires tremendous amount of energy to start off with, but it's the sun, it has enough energy. Once it does that, it forms helium, and then that releases a tons of energy. Yeah, remember, to form bonds, energy is release, a lot of energy release. Now that energy is enough to catalyze another reaction. So this is what happens in a hydrogen bomb. It's called a fusion bomb. Yeah, you give it enough energy to start off, and it produces so much energy that the rest of the compounds are also formed. Well, not in a controlled environment like what we could do in a lab, obviously. Well, you and I can't do it in a lab. You need a very hi-fi lab, and nobody around for a lot of kilometers. Um, so the sun, in short, is a huge hydrogen bomb. Scary? Well, it still works. All right. Any doubts about the periodic table so far? This particular simulation of the periodic table? Okay. I'm going to pause this and go on to the moves. I'm going to move on to the next simulation in that case. No, Jacob, fusion, not fission. Fission is breaking. Fusion is coming together. Okay. So we're talking about nuclear fusion. Is that clear? All right. Cool. So in this, we will try and learn about something called isoelectronic species. Sounds like a scary word. It's really not. Iso means same. Electronic, well, means electronic. Species is, well, all of these guys. Why do I call them same electron species? Because all of them have the same number of electrons, irrespective of proton, neutron, all. They basically have the same number of electrons. Okay? Do you see that? They all basically have the neon configuration. We'll learn that in detail. So right now we're looking at the neon configuration, hence that's selected. There are many ions over there. We are talking about the sodium ion. That's one that's selected. This thing in the middle over here shows the electronic configuration. Okay, and Na plus happens to have a neon configuration. Is this clear? Just look at this. It's very straightforward. Nothing very fancy at this point. All right. So you guys know that metals tend to lose electrons to achieve noble gas configurations. Duplet, octet, duplet in case of hydrogen, octet in case of everything else. Non-metals gain electrons, do the same thing. So this is how we actually identify them. So let's select the first one, yeah, helium to be the noble gas. And it has 2 electrons in the outermost shell. That's it. Neon clearly has 8. Yeah, 8 and 2. 8 in the outermost, 2 before. So it's total of 10 electrons. Okay? Simple enough? Okay. Let's look at the oxide anion. It has an atomic number of 8. Oxygen has an atomic number of 8, so it must have 8 electrons. So it must gain 2 electrons to reach the neon configuration, or lose 6 electrons to reach the helium configuration. Clearly, the second seems to be a ridiculous thing to do, because remember, energy required to break bonds, energy released to form bonds. So I have the option of giving it enough energy to lose 6 electrons, or somehow overcome the repulsion of other electrons and add 2 more electrons, which would eventually make the thing stable. So oxygen decides to do the latter and accept 2. Yeah, exactly, it does that. And clearly, this means that it's non-metallic. Do the same exercise with fluorine or fluoride anion. Atomic number is 9. It has 2 electrons and 7 in the outermost. So again, it can lose 7 or gain 1. It chooses to gain 1. This also is non-metallic. Clear? So far so good? Okay. So what I can do next is go to the next, yeah, simple thing, Na plus. Atomic number is 11. It can lose 1 or gain 7. In this case, obviously losing 1 is more sensible. Hence it becomes a cation. So this is a metal. This is how nature decides what's a metal and what's a non-metal. Yeah, really simple stuff. Clearly, you guys can play around with this. It's pretty interesting. Magnesium does the same thing. Sulfur in the next one is exactly like oxygen. Chlorine is similar to fluorine, and then you can have other things like calcium, which is similar to magnesium. A lot of funky things. Selenium again, same oxygen family. Bromium is in the chlorine family. So you can easily figure out which ones are metal and which ones are non-metal. Do you guys have any doubts in this particular simulation? It was not very difficult, which is why I went quickly through this. But if you guys want me to explain this further, please ask. Do not hesitate. Let me know if you guys want me to explain this further. I'll give you guys the link to the simulation as always. You guys can play around with this. Pretty cool stuff. And you can also download this 4s2 3d10. Ah, okay, cool. That talks about. It's very interesting that you asked. These are called subshells. The number 4 is talking about the fourth shell. S and P and all of that refers to subshell. What is a subshell? It has to do with the shape of the. You know that electrons exist in pairs. That you don't know that, but I'm telling you that now. Electrons always exist in pairs. Like the Earth, if you guys want me to stop at any point, ask me to. This is not a part of. Let me stop this simulation. Let me stop this, and I will answer this in class. Okay? Yeah, just one moment. Do you have any questions regarding the simulation at this point? Okay, let me just pause or just stop this recording, and then I will get back to class and I will explain. Yeah, one moment.